welcome to the Deep Dive. Today, we're really going deep, plunging into, well, frankly, the world's biggest and maybe most complicated machine ever built, the Large Hadron Collider. You know it as the LHC. We're talking about a place that's, depending on where you look, the hottest spot, the absolute coldest place, the fastest racetrack, and maybe the most precisely engineered environment humans have ever put together.
Okay.
So, our mission today, we've got a whole stack of source materials here detailing the unbelievable engineering, the Nobel Prize science, the discoveries, and maybe the most surprising part, the way this thing has impacted your daily life. We want to boil all that down, give you the real inside scoop. This isn't about profit, right? It's pure curiosity, trying to figure out the universe's biggest secrets.
It really is the ultimate quest for knowledge. And what I find so fascinating beyond the physics is just the sheer scale and the spirit of the place. CERN, the European Organization for Nuclear Research, which runs the LHC, it's so much more than just this giant underground ring.
Right.
It sits right there on the Franco-Swiss border near Geneva. And it's basically this huge global village for science. You've got thousands of scientists, engineers, technicians coming from over 110 different countries.
Wow, 110.
Yeah, think of it like a massive international university. but laser-focused on particle physics. And its purpose is kind of twofold. One, obviously, is the fundamental research, smashing particles to bits to see what the universe is really made of.
The core science bit.
Exactly. But just as important, it stands as this powerful symbol of unity. It really shows that people from all over, different cultures, different languages, even from countries that might not get along politically, they can work together when the goal is just advancing human knowledge for everyone.
Okay, let's try and get our heads around this world's largest machine thing, because honestly, the engineering behind it is almost as mind-blowing as the physics they're trying to uncover. Let's start with the physical size. We're talking a 27-kilometer ring that's, what, just under 17 miles around?
That's right.
If you tried to overlay that on a city map, it would just swallow huge chunks of it. But you can't see it, right? It's all underground.
Completely. It's buried deep, typically around 100 meters down. That's nearly 300 feet below the surface.
Why so deep?
Well, a couple reasons. First, you get incredible geological stability down there. When you're trying to align magnets over miles with, micron level precision, you don't want things shifting around.
Makes sense.
And second, the Earth itself provides natural shielding, both from things like cosmic rays interfering with the experiments and also shielding the surface from the experiments themselves. It's basically this massive hidden monument to precision engineering.
Okay, so huge ring, deep underground, and the name tells the story. Large Hadron Collider. Let's break that down. Hadron?
Right. Hadrons are a category of subatomic particles. The ones they use mostly in the LHC are protons, the basic nucleus of a hydrogen atom. They just strip the electron off simple hydrogen gas. Sometimes, though, for specific experiments, they use heavier ions, like lead ions, which are also hadrons. They strip these particles off in smaller accelerators, kind of like on-ramps, building up speed.
Right, getting them going.
Exactly. Before injecting them into the main 27-kilometer ring. And once they're in there, they really step on the gas. They push them up to almost the speed of light. We're talking 99.9999991% of light speed.
That number is just absurd. Okay, so that's the hadron part. What about collider?
That's the action part. They don't just send one beam around. They create two separate beams of these hadrons, traveling in opposite directions inside their own vacuum pipes.
Two beams, opposite ways. Got it.
Then, at specific points around the ring, 4 main locations where the big detectors are, like ATLAs and CMS, they use powerful magnets to steer these two beams into head-on collisions. Smash.
And that's the moment they're interested in.
That's the whole point. When these protons, traveling at nearly the speed of light, collide, the energy released in that tiny point momentarily recreates the conditions that existed just fractions of a second after the Big Bang. It's like winding the clock back 13.8 billion years in a controlled way.
I read this analogy in the source material that just floored me. It said, making these particles collide is like firing two needles 10 kilometers apart with such precision that they meet halfway.
Yeah, that captures it pretty well.
The level of control needed for that, it's almost unbelievable.
It really is. It pushes engineering right to the absolute edge. And the key technology, the real heroes that make this possible, are the superconducting magnets.
Ah, the magnets, right.
They absolutely need them. First, just to bend the beams around that 27-kilometer circle. Keeping particles moving that fast in a curve requires immense force.
How many are we talking about?
Thousands. The total count is 9,593 magnets. The big ones are the 12,232 main dipole magnets. They're each 15 meters long, like the length of a bus.
Wow.
And their job is just to provide that constant bending force, keeping the beams on track around the ring. But then you also have 392 quadrupole magnets. They're a bit shorter, 5 to 7 meters.
And what do? Focus the beam.
Exactly. They squeeze the particle bunches down, make them incredibly dense right before they reach the collision points. That's how they achieve that needles meeting halfway kind of precision.
Yeah.
They focus the beams down to the width of a human hair just before impact.
Okay, so you've got these particles flying around at insane speeds, generating incredible energy. But I also read the LHC is one of the coldest places in the known universe. How does that work? That sounds like a total contradiction.
It does, doesn't it? But that's the central engineering challenge and maybe the most amazing part. The cooling. To get those magnets to work properly, they need to be superconducting.
Meaning zero electrical resistance.
Precisely. And to achieve that state with the materials they use in niobium titanium alloy, you need to get them incredibly cold. The entire 27-kilometer ring of magnets has to be chilled down to just 1.9 Kelvin.
1.9 Kelvin.
Yeah.
What's that in Celsius?
That's minus 271.3 degrees Celsius.
Minus 271, so colder than outer space.
Yep. Deep space is about 2.7 Kelvin. So the LHC is officially colder than interstellar space, buried 100 meters underground. It's kind of mind-bending.
That is just wild. How do they even maintain that over 17 miles?
With a truly colossal system using liquid helium, it's this incredibly complex, decentralized cryogenic network. Thousands and thousands of liters of superfluid helium are constantly circulating, keeping everything at that precise ultra-low temperature.
Superfluid helium.
Yeah, helium behaves very strangely at those temperatures. It becomes superfluid, meaning it can flow without any viscosity, which actually helps distribute the cooling efficiently, but maintaining it is a huge task. If the temperature rises even tiny bit in one section, the magnets can lose their superconductivity in what's called a quench.
And that's bad.
Very bad.
Yeah.
It releases a massive amount of stored energy very quickly. So the systems to keep it stable and detect any...
Okay, so they managed to steer these impossibly fast particles and keep everything incredibly cold. Then the collisions happen. The challenge must immediately shift, right? From physics control to data.
Instantly. You've created this tiny fireball mimicking the Big Bang. Now you have to capture what happened. The detectors surrounding the collision points are these gigantic, multi-story digital cameras, essentially.
But recording everything.
That's the problem. It's impossible. Every time the beams cross, which happens millions of times per second, potentially hundreds of particles fly out. If they recorded everything, the data volume would be beyond astronomical. We're talking something like a petabyte of raw data per second.
A petabyte per second. That's insane.
It is. So they have these incredibly sophisticated electronic trigger systems. They analyze the collision debris in real time, in fractions of a second, and decide if an event looks potentially interesting, like it might contain evidence of a rare particle or process.
So they filter it on the fly.
Massively. They throw away almost everything. They might select only, say, 100 to 1,000 of the most promising events per second to actually record for later analysis. Even with that filtering, the CERN data center still ends up storing over 30 petabytes of processed data each year just from the LHC.
30 petabytes a year, let's put that in perspective again. That's like 1.2 million Blu-ray discs or 250 years of HD video.
Something like that, yeah. It's an enormous amount. And they permanently archive even more, over 100 petabytes on tape systems.
So how do the thousands of scientists actually use this flood of information? They can't all be downloading petabytes to their laptops.
No way. That's where another huge innovation comes in. The worldwide LHC computing grid is basically a global network connecting hundreds of computer centers in, I think, over 40 countries now.
A distributed supercomputer?
Kind of. The data from CERN gets distributed out to these centers, Tier 1 and Tier 2 sites, allowing scientists anywhere in the world to access and analyze the portion of the data relevant to their research. It's a massive collaborative computing effort.
And the sheer demand must push computing technology forward, right? Storage, networking.
Absolutely. The LHC has been a major driver for advancements in grid computing, high-speed networking, massive data storage solutions, and distributed data analysis techniques. The tech industry definitely benefits from the problems CERN have to solve. So yeah, the engineering marvel creates this equally impressive computing marvel.
Okay, so we have the biggest machine, the coldest temperatures, the fastest particles, the most data. All of this incredible infrastructure built for one reason, to ask the most fundamental questions we can about reality, which leads us perfectly into the core mission. When people talk about the LHC's biggest success, one thing always comes up. 2012, the announcement of the Higgs boson. For you listening, this wasn't just finding some random new particle. This was like the keystone for the entire structure of modern particle physics, the Standard Model.
That's absolutely right. The Standard Model, which physicists put together back in the early 1970s, was amazingly successful. It described all the known fundamental particles, quarks, electrons, neutrinos, and the forces between them, except gravity. But it had this one huge, glaring hole.
Which was?
Mathematically, the simplest version of the model predicted that all fundamental particles should have zero mass. They should all be like photons zipping around at the speed of light.
They're not. We have mass. Things have mass.
Exactly. If everything was massless, atoms couldn't form, stars wouldn't ignite, planets wouldn't hold together, we wouldn't exist.
Yeah.
The universe would just be this undifferentiated soup of energy. So clearly, the model was missing something crucial about why particles have mass.
And that's where Peter Higgs and others came in, with this idea of a field.
Yes, back in the 1960s, theorists like Peter Higgs, Francois Englert, Robert Brout, and others proposed this really elegant, though kind of abstract solution. They suggested that the entire universe is permeated by an invisible energy field, now called the Higgs field.
Okay, an invisible field everywhere. How does that give things mass?
The idea is that particles acquire mass by interacting with this field. Think of it like, imagine wading through thick syrup, or maybe like trying to move through a crowded room at a party.
Okay.
Some particles, like photons, don't interact with the field at all. They just nip right through, like someone nobody notices at the party, so they remain massless and travel at light speed.
Right.
Other particles interact with the field very strongly. They get dragged back by it, like the most popular person at the party who keeps getting stopped to talk. This interaction, this stickiness, is what we perceive as the particle's mass. The more it interacts, the heavier it seems.
So a really heavy particle, like a top quark, is just interacting a lot with this Higgs field.
Exactly. And the Higgs boson, the particle they discovered at the LHC, isn't the field itself, but rather an excitation of it, like a ripple or a wave passing through that universal field. Finding the Higgs boson was the proof that this whole mechanism, this field, was real.
And without it, the universe as we know it just wouldn't be possible. Stars, planets, us, none of it.
Pretty much. It was the missing cornerstone. Its discovery beautifully confirmed the Standard Model and explained the origin of mass for fundamental particles. That's why Englert and Higgs got the Nobel Prize in Physics in 2013. It was a monumental achievement.
But finding the Higgs wasn't the end of the story for the LHC, was it? I mean, it's still running, planned for another 20 years or so?
Not at all. Finding the Higgs confirmed the Standard Model, but it also highlighted its limitations. The Standard Model, even with the Higgs, is incomplete. There are huge cosmic mysteries it just can't explain. So the search continues.
And they use the machine in different ways to probe these other mysteries, right? I read about them using lead ions sometimes instead of protons.
That's right. For a few weeks each year, they switch things up. Instead of colliding individual protons, they accelerate and collide entire lead nuclei, which are much heavier, packed with protons and neutrons.
Why do that? What does colliding big, heavy things tell you?
When these heavy ions smash together at high energy, they create this incredibly hot, dense state of matter, literally trillions of degrees. It's called a quark-gluon plasma.
Quark-gluon plasma. Sounds exotic.
It is. There are several, but maybe three stand out as the biggest targets right now. First, and probably the most profound, is the mystery of dark matter and dark energy.
Right, the stuff that makes up most of the universe, but we can't see.
Precisely. All the stars, galaxies, gas, dust, everything described by the Standard Model only accounts for about, well, maybe 4 or 5% of the total mass and energy content of the universe.
Only 4%. That's tiny.
It is. Astronomical observations, like how galaxies rotate and how light bends around massive objects, tell us there's much more stuff out there. About 23% seems to be dark matter, some kind of invisible matter that interacts gravitationally, but not through light. And then a whopping 73% is dark energy, this even more mysterious force causing the expansion of the universe to accelerate.
And the Standard Model has nothing to say about these.
Basically nothing. It doesn't contain any particle that fits the description of dark matter. So a major goal for the LHC is to try and create dark matter particles in the collisions. If certain theories beyond the Standard Model are correct, these particles might be produced, but because they don't interact much, they'd fly out of the detectors unseen.
So how do you detect something invisible?
Indirectly. You look for events where there's a lot of energy and momentum missing, suggesting something invisible carried it away. Finding evidence for such particles would be absolutely revolutionary for cosmology.
Okay, dark matter and dark energy, huge mystery number one. What's number two?
The second big area is the search for supersymmetry, often called SUSY.
SUSY, I've heard that term. It sounds like more symmetry.
In a way, yes. COA is a very elegant, though still hypothetical, extension of the Standard Model. It proposes a new kind of symmetry in nature, suggesting that every known fundamental particle has an undiscovered, heavier superpartner particle.
So every quark has a squark, every electron has a selectron.
That's the idea. For every fermion matter particle, there's a corresponding boson, force carrier, and vice versa, with these new superpartners. It sounds a bit wild, but CERN is attractive to theorists for several reasons.
Like what?
Well, for one, it could potentially solve some deep theoretical problems within the standard model itself, like why the Higgs boson has the mass it does, the hierarchy problem. It also offers a path towards unifying the fundamental forces, electromagnetism, the weak force, and the strong force at very high energies.
Bringing the forces together, like Einstein was trying to do.
Sort of, yes, pushing towards a grand unified theory. And maybe most intriguingly, the lightest, most stable hypothetical CERN particle would be an excellent candidate for dark matter.
Ah, so CCUS could solve two problems at once.
Potentially, yes. That's why the LHC is pushing to higher energies, like the 13 TeV runs. If these superpartner particles exist, they're likely very heavy, and you need that much energy to create them. So far, no definitive sign of CERN has been found, but the search is definitely still on.
Okay, so dark matter energy, supersymmetry. What's the third big puzzle?
This one is really fundamental to our existence. The matter versus antimatter imbalance.
Right, the universe seems to be made of matter, but shouldn't the Big Bang have made equal amounts of matter and antimatter?
According to our best theories, yes. For every particle created, an antiparticle with the opposite charge should also have been created. But if that happened perfectly, then as the universe cooled, all the matter and antimatter should have met and annihilated each other, leaving behind nothing but pure energy, a universe filled only with light.
But we're here. Clearly that didn't happen.
Exactly. We exist, galaxies exist, it's all made of matter. So somehow there must have been a tiny imbalance right at the beginning. Maybe for every billion pairs of matter and antimatter particles, there was just one extra matter particle left over. That tiny fraction survived the annihilation and became everything we see today.
So the question is why? Why that slight preference for matter?
That's the mystery. The standard model does allow for a small amount of asymmetry between matter and antimatter, something called CP violation, but not nearly enough to explain the universe we observe. So physicists at the LHC, especially in experiments looking at the decays of specific particles like B mesons, are searching for new sources of matter-antimatter asymmetry, phenomena that go beyond the standard model. Finding that would be another profound discovery about why we're even here to ask the question. It's really important to connect these incredibly abstract, fundamental questions back to, well, the real world. Because the effort needed to build and run something like the LHC has this amazing way of spinning off technologies that change our everyday lives.
It's not just about finding exotic particles, then.
Not at all. The value of this kind of blue sky research often comes from the unexpected practical benefits. To solve the immense technical challenges of the LHC, engineers and scientists have to invent things, and sometimes those inventions turn out to be incredibly useful elsewhere.
And the absolute classic example, the one everyone knows, even if they don't realize it came from CERN, has to be the World Wide Web.
It's almost unbelievable, isn't it? The foundation of the modern internet, born in a particle physics lab in Switzerland.
How did that even happen? What was the connection?
It goes back to that data problem we talked about. In 1989, a British scientist working at CERN named Tim Berners-Lee was trying to solve a very practical issue. How could the thousands of scientists collaborating on CERN experiments, but based at universities all over the world, easily share their data, notes, research papers, and results?
Right, the collaboration challenge.
Exactly. Before the web, sharing information between different computer systems, often using different software, was a total nightmare. Berners-Lee proposed a system using hypertext, the ability to link documents together, and developed the key protocols and software. URLs to address documents, HTTP to transfer them, and HTML to write them.
He basically invented the first web browser and web server.
He did. And crucially, CERN made the decision to release the technology into the public domain for free with no patents. They weren't trying to make money, they were just trying to solve their scientific communication problem. And by doing so, they gave the world this incredibly powerful tool that has reshaped, well, everything.
It's just a stunning example of unintended consequences in the best possible way. A need for scientists to share data leads to the global internet as we know it.
And that legacy continues. The sheer scale of LHC data, those 30 petabytes a year, keeps pushing the boundaries of computing.
How so?
Well, the worldwide LHC computing grid we mentioned earlier, that global network, it was one of the first and largest examples of grid computing, which was a precursor to modern cloud computing. The techniques developed to manage, distribute, and analyze that massive data set have influenced everything from financial modeling and weather prediction to bioinformatics and large-scale internet services.
So the need to handle the physics data constantly drives innovation in IT.
Constantly. They're always needing faster networks, bigger storage, more efficient processing, better data security. It acts like a high-pressure cooker for developing solutions that eventually benefit the wider tech world.
Okay, the web and computing are huge, but the sources also mention very direct impacts in fields like medicine.
Yes, that's another really important area. The technology developed for the detectors at the LHC, the instruments that actually see the particles coming out of the collisions, has found direct application in medical imaging.
How does detecting a quark relate to looking inside the human body?
It's about the sensitivity and precision needed. The detectors have to track tiny bursts of energy from high-speed particles with incredible accuracy. This requires very sophisticated sensor materials like scintillating crystals that give off light when a particle passes through, and highly sensitive light detectors. Well, that same core technology detecting faint signals from particle interactions is directly used in PT scans, positron emission tomography.
PT scans for cancer detection.
Exactly. PET scans work by detecting pairs of gamma rays emitted indirectly by a radioactive tracer introduced into the body. The detectors used in modern PET scanners are, in many ways, direct descendants of the detector R&D done for high-energy physics experiments at places like CERN. So the quest for fundamental particles has literally given doctors better tools to find and fight cancer.
That's a really powerful connection. What about other industries? Those magnets, the cryogenics, surely that tech spills over too.
Absolutely. The demand for thousands of powerful, reliable superconducting magnets pushed the development of superconducting wire and magnet technology forward significantly. This benefits other areas that use high-field magnets, most notably MRI machines, magnetic resonance imaging, in hospitals, which rely on similar superconducting technology.
Okay, better MRIs too.
And the expertise developed in cryogenics, keeping things colder than outer space reliably over huge distances, is valuable for any industry needing ultra-low temperatures, from material science research to potential future applications like superconducting power lines. Similarly, the need for ultra-high vacuum systems, advanced electronics that can survive radiation, and incredibly precise metrology, measurement techniques, all drive innovations that find their way into aerospace, manufacturing, and other high-tech sectors.
It seems like almost every extreme engineering challenge at the LHC forces an innovation with broader uses.
That's often how fundamental science works. You push the limit for one reason, and you end up creating tools and knowledge that benefit many other areas.
And maybe one of the biggest but hardest to measure impacts is just the people, the scientists and engineers trained there.
That's a crucial point. CERN isn't just a lab. It's arguably one of the world's premier training grounds for scientists and engineers. You have thousands of students, postdocs, young researchers from all over the globe coming to work on arguably the most complex machine ever built. They're not just learning physics theory. They're learning how to design detectors, write complex software, manage huge projects, troubleshoot high-tech equipment, and perhaps most importantly, how to collaborate effectively in large international teams on incredibly difficult problems.
So they gain skills that are valuable anywhere.
Immensely valuable. When these highly trained people finish their time at CERN and move on, whether to academia or into industry, they take that unique expertise with them. They might go work in aerospace or medical technology or computing or finance, and they bring that high-level problem-solving ability and collaborative experience. It's a massive transfer of knowledge and human capital back into society worldwide. Now, given the sheer scale of the LHC and the, let's face it, pretty abstract nature of the science, it's natural that some common questions and misconceptions arise in the public mind. It's probably good to address a couple of those directly.
Yeah, let's do that. Maybe the most sensational one first.
Yeah.
The infamous black hole myth. The idea that the LHC could accidentally create a tiny black hole that might, swallow the Earth. It sounds like science fiction, but it grabs headlines.
It does grab headlines, but thankfully, the physics just doesn't support that fear at all. We need to be really clear about this. The energies reached in LHC collisions, while high for a man-made accelerator, are actually far lower than energies found in nature.
Lower than nature? How?
Cosmic rays, basically protons and other particles accelerated by things like supernovae or active galactic nuclei, are constantly bombarding the Earth's upper atmosphere. And some of these cosmic rays hit with millions of times more energy than the collisions inside the LHC.
Millions of times, wow.
Yes, And this has been happening for billions of years, striking the moon, striking other planets. If high-energy particle collisions could create dangerous, stable black holes, the universe would have popped them out constantly. The fact that Earth and the moon are still here is pretty solid experimental evidence that it's safe.
So the LHC is just doing in a controlled way what nature does randomly, but with much less energy.
Exactly. Any theoretical micro black holes that might be created, and this is highly speculative physics itself, would be incredibly tiny and would evaporate almost instantly due to Hawking radiation. They pose absolutely zero threat. It's pure sci-fi fear-mongering.
Okay, good to get that clear. The other big one is the cost. People see this gigantic machine, thousands of people, and think it must cost astronomical sums, maybe taking money away from other things. The expensive myth.
It's definitely not cheap, let's be honest. Building the LHC itself cost around 4.3 billion Swiss francs, spread over many years and many countries. That's a significant investment.
Right.
But it's important to put it in perspective. That construction cost is comparable to, say, hosting an Olympic Games or building a major airport terminal. And the annual operating budget of CERN as a whole is often compared to that of a medium to large-sized international university.
So significant, but maybe not outrageous compared to other large-scale public or scientific endeavors.
Exactly. And crucially, you have to weigh that cost against the value generated. We've already talked about the spin-offs, the World Wide Web, PT scans, advances in computing, trained personnel. The economic and societal benefits derived, arguably, far outweigh the investment over the long term.
It's an investment in knowledge and capability, not just a running cost.
Precisely. It's framed as an investment in fundamental understanding and the technological capacity that comes with it. And it's an investment shared by many nations.
That collaborative aspect seems key. It's not just one country footing the bill or reaping the reward.
Absolutely. That global commitment is fundamental to CERN's identity. Having scientists and funding agencies from over 110 countries involved, it's a remarkable model.
Especially today, with global tensions.
Right. You have people from nations that might be politically hostile towards each other, working side by side in the control rooms, analyzing data together, focused entirely on the shared scientific goal. It really is a living example of science diplomacy and how humanity can unite around common objectives like advancing knowledge.
It's a powerful counter-narrative. And this collaboration isn't just a one-off, right? The LHC has been running for a while and plans to keep going.
Oh, yes. It's a long-term project. The first proton beam circulated back in September 2008. They had the first high-energy collisions at 7 TeV, tera-electron volts, in March 2010.
And they've ramped it up since there?
Considerably. Run 2 operated at a collision energy of 13 TeV. And they're currently working towards a high-luminosity LHC upgrade, or HL-LHC.
High luminosity, meaning more collisions.
Exactly. The goal is to significantly increase the rate of collisions, the luminosity. This means generating much more data over the next couple of decades, vastly increasing the chances of observing very rare processes or discovering new, potentially very heavy particles associated with things like dark matter or supersymmetry. It's about statistics. The more collisions you see, the better your chance of finding that needle in the haystack.
So the discovery potential is still huge. What about the practical side, like power consumption? A machine this big must use a lot of electricity.
It does. CERN's total energy consumption is around 1.3 terawatt hours, TWh, per year, when the accelerator complex is running full tilt.
That sounds like a lot.
It is a significant amount, roughly comparable to the energy usage of all the household in a city like Geneva. However, again, context is important. It's still only a tiny fraction, much less than 0.1% of the total electrical energy produced across the European Union. And CERN works hard to manage this, for example, by scheduling operational downtime during peak winter energy demand periods. It's a necessary cost for running this unique global facility. #global facility.
#outro.
All right, so that brings our deep dive into the Large Hadron Collider towards its conclusion. We've covered a lot of ground, literally 27 kilometers of underground tunnel. We talked about the engineering extremes operating colder than outer space at 1.9 Kelvin.
Pretty amazing stuff.
The discovery of the Higgs boson finally cracking the mystery of mass within the standard model, but also how this fundamental quest led to incredibly practical things we use every single day.
Like the World Wide Web. Hard to overstate that one. Or PET scans, saving lives in hospitals. The LHC at CERN really does feel like more than just a science experiment. It's this testament to human curiosity, our ability to cooperate on a massive scale, and just the sheer audacity to build something like this to ask the biggest question.
It truly is. And as we wrap up, maybe the most striking thought, the real takeaway for me, comes back to that paradox of scale we kept bumping into.
How so?
Well, the whole endeavor is focused on the tiniest constituents of reality, right? Subatomic particles, fleeting interactions, probing the quantum realm, searching for things like dark matter or maybe hints of extra dimensions. The absolute smallest scales imaginable.
Right, the micro world.
Yet the technology developed specifically to probe that infinitesimally small world, particularly the need to share vast amounts of data globally, led directly to the invention of the World Wide Web. The technology that more than anything else connected the entire planet on a macro scale.
Smallest scale science leading to the largest scale connection.
Exactly. It's this incredible demonstration that sometimes the most abstract, curiosity-driven research, the quest for knowledge, seemingly furthest removed from daily life, can yield the most profound and immediate practical advancements for all of humanity right back here on Earth. It makes you wonder what today's fundamental questions will lead to tomorrow.